So technically this isn't a proof for 1 times 1 equals 1, but it is a proof of a statement related to that idea. So this is saying that over an associative binary operation, in our example of 1 times 1, that binary operation is multiplication on a set S. In our example, that set is going to be the set of all real numbers except 0, or rather except when the divisor is 0, but we'll get into that. But see, the operation, let's say multiplication, it must contain one identity element, and we could prove this statement as follows here. So for part A, you assume that there's more than one identity element, and then you show by definition of the identity, E times E prime must equal E prime, and E times E prime must equal E. Therefore, E equals E prime. Therefore, there's only one identity element. Furthermore, you get into like the second statement. For any identity element, any element of S has at most one inverse. Now we can move on from it, but this is an example or demonstration of using the definition of an identity to prove a statement or claim. And in our case, this equation E times E prime equals E is logically equivalent to 1 times 1 equals 1, because E equals E prime. So it's the same. So it's basically saying E times E equals E. It's not any different. So here's the definition of an identity. For an element in S, let's call it the identity element, it must satisfy the equation A times the identity equals A, or the identity times A equals A. So it's commutative for any A in S. So you could just think of that as any number in the set of all numbers, right? Think about multiplication. Like let's say we define, this is how this is the set of that the binary operation of multiplication is defined on, which is m over n for any integer m and n. So this Z is a set of all integers, such that n is non-zero. So m can be 0, but n is not 0. And so this is why division by 0 is undefined in multiplication, because division is just multiplying by the inverse element, right? It's not actually division. It's kind of like hot and cold. Cold is the absence of heat. Division is the inverse operation of multiplication. It's not. I wouldn't even call it an actual operation, but I mean that's how we understand it in school. But I would actually consider, it's just multiplying again, but instead of multiplying by a number that isn't by any other number, it's specifically for the multiplicative inverse. But what if we change our set, right? What if we had x is less than 0, like for any real number? So that means every number in our set is going to be a negative number. That actually won't exhibit closure, because if you take any number in that set times another number in that set, you're going to get a number outside of the set, because a negative times a negative is a positive. Let's look back. So what's closure? Closure essentially means that for any element in the set, the binary operation performed on those two elements is well defined and in the set. So that's considered. So in order for a set and a binary operation, in this case, let's say the real numbers on multiplication, which is what is coming from that 1 times 1 equals 1. These conditions must be satisfied to be considered a group. And so, like, this is just a start. We want to get into that's how we classify it as a group, and that's how we can use it practically, or rather in application. But this is a generalization of all sets over operations. Whether it be addition or multiplication or modulus 2. So this is the checklist when you want to determine if a set over an operation, a binary operation, is a group. So, say the set of real numbers over multiplication, if that's a group, it must satisfy these 4 conditions. Going back to our other example, where you have, let's say the set of real numbers less than 0, so that's all negative numbers over a multiplication. Is that a group? No, because it doesn't satisfy closure, which is the first condition. In group theory, our primary objective is to, study the algebraic properties of those elements on that operation. And then, obviously, we can get some practical application out of that, in engineering or any other field of science. So then going back to, like y0 is undefined, there is no multiplicative inverse for 0, such that this equation is satisfied. There's no element that we can take out of, let's say, the set of real numbers, whether it's negative or positive, and get the identity element 1. So, this is why 0 is undefined. It's not just like someone said, hey, 0 is undefined, and you have to accept that. There's a reason why 0 is undefined. It's because it doesn't satisfy. Because if we included 0 in the set, then the set of real numbers over multiplication would not be considered a group. And this, this is just the third chapter of this book on called Abstract Algebra. The group is kind of like the foundation for getting into like polynomials, commutative rings, fields, structures, Galois theory, just different like things that we're familiar with in mathematics in grade school. None of that would work if we included 0 in that set. So